Hey everyone, Mr. Huck here. I went ahead and decided to make my own key to the 4.5 through 4.8 quiz review. And instead of having this video take, close to an hour and working everything from scratch, I'm just going to go problem by problem and talk about my solutions on this key. That way you're still getting my thought process as how I would approach these problems. And this video hopefully won't take as long as it originally would have. So I'm going to go ahead and get started. Part A, tigers are an endangered species. In 2015, there were approximately 3,200 tigers worldwide. Because the tigers were verging on extinction, many countries began protecting them. This helped to increase the population by 40% over the 7 years since 2015. So we have a three-part problem. The first part is to approximate the number of tigers in 2022. Second, write an equation with a fractional exponent giving the tiger population for any year during the 7-year growth period. We're going to name the equation T of n. And then using our equation, predict the number of tigers in 2018, rounding to the nearest whole number. I'm actually going to go out of order. When I solved this problem, I did part B first, and then I used my equation from part B to do part A. So what I'm noticing here, 3,200 tigers worldwide in 2015. So that's our initial population. That's why you see my 3,200 right here. And we can see that the tiger population was increasing by 40% over that 7-year time period. So if it's an increase, we do 1 plus, and then we take our increase rate and turn it into a decimal, so 40%, 0.40. So we have 1 plus 0.4, and notice that it was over a 7-year period of time. That's why we have t over 7. So this function here is saying initial population of 3,200 tigers increasing by 40% over a 7-year period of time. All right, did we use our equation from part B? We look at part A, approximate the number of tigers in 2022. Okay, well, 2022 was 7 years after 2015. You can plug the 7 in. Notice that when you plug it in to the exponent here, 7 over 7 is just 1. So 3,200 times 1.4 to the first power, you get 4,480 tigers. And then same deal in part C. Now you're trying to predict the number of tigers in 2018. 2018 is 3 years after 2015. So plug in a 3 to your equation from part B, and you get approximately 3,696 tigers. All right, part B. The graph of a function f is shown. Write an equation that could be used to model f. So there are multiple correct answers here. I'm just going to take you through my thought process for one of the potential correct answers. So what I really like to do when I'm writing equations from a graph or an exponential, I like to know the y-intercept. So I noticed, we have this point 211, we have this point 4, 85. If I shifted this graph to the left 2, then I would have a y-intercept at 0, 11, and I'd have this point as 2, 85. So what I did is I took this new line and I found an equation for this line that would have a y-intercept at 0, 11. So we can see here, y-intercept at 11. Now we got to figure out the common ratio from 0, 11 to 2, 85. So that's saying 11 times 2 common ratios, that times r, or times r squared, would get us to 85. Divide both sides by 11, take the square root to get rid of the power 2, and we get 2.7798. Okay, so before shifting to the right 2, so this function that I have here in blue, this equation models that function. Then if I want this line, an equation for this exponential line, I just take my equation that I found for this blue one, and I just shift it right 2. So I take my equation, shift it right 2 means I would have a minus 2 in the exponent. So that's how I handled it, and it works well. All right, part C. The mass of a sample of phosphorus-32, a radionuclide commonly used in biochemical research, can be modeled by the function right here. Where m of t is the mass of the sample after t days, we want to find the half-life of phosphorus-32. Okay, so when we see half-life, if we run into any half-life problems, well, for half-life, remember half-life is the amount of time it takes for a substance to decay by half of its original amount. which means we would want this base to be a 1/2, not a 1 over 32. Well, if you take 1/2 and you raise it to the 5th power, so 1/2 times a half times a half times a half times a half, 1/2 to the 5th power is 1 over 32. So I can rewrite this function as this, replacing the 1 over 32 with 1/2 to the 5th power. Then using exponent rules, if I have 1/2 to the 5th power being raised to t over 71.5, then I can take this exponent and multiply it out here. So now I have 175, base of 1/2, raised to the 5 times t over 71.5. And this whole part, like imagine if the 5 wasn't there. This would mean we have a half-life every 71.5 days. If I multiply by 5, that means I have 5 half-lives every 71.5 days. So to find one half-life, take 71.5, divide it by 5. That means we have a half-life of 14.3 days. All right, part D. A family of 6 mice can multiply into a family of 60 mice in a mere 3 months. Write an equation for m of t, the number of mice in the family after t months, where m of 0 equals 6. Okay, so we're going from an original population of 6 mice to a population of 60 mice over the course of 3 months. So 6 to 60, that's multiplying by 10, but it takes 3 months to do it. So a function that we could write, we could have something like this. Initial population 6, it's multiplying by 10, but it takes 3 months. So we compensate by having t over 3. This is for the every 3 months part, and that equation will model that scenario. All right, part E. This one can be tricky if you don't know your exponent rules. However, if you have access to a graphing calculator, then this one is very simple because you could just graph them all and see which ones match. Okay, so the graph of function f is shown. Which of the following equations represents f? Choose all that apply. As you can see, 4 of them are going to, all 4 of these are equivalent to each other using different exponent rules. So what I did first, I came over and I just decided, let me get the simplest function that models this graph. So I noticed it's decay, obviously it's decreasing. Okay, so it's definitely decay. That means our base is going to have to be between 0 and 1. And we have a y-intercept at 0, 4. And we have another easy identifiable point at 1, 2. Okay? So y-intercept of 4. And when you go to the next x value from 0 to 1, we can see that 4 to 2 is multiplying by a half. So I can see that my base is a half. All right? So I know that this is an equation, not the only one, but this is an equation that could model that graph, which also just so happens to be option 3. So I know option 3 is correct. Option 1, so now we're going to go option by option. So option 1, it has the correct base of a half, and it has to the x power, but it's option 1 is saying that your y-intercept is at 1, which it's not. Y-intercept's at 4, so that one's wrong. Option 2 is exponential growth. Yeah, that's not going to work. So 2 is wrong. 3, we've already talked about why 3 is correct. Option 4, if we use some exponent rules, we'll see why option 4 is the same thing. This 1/2 to the x plus 1 power, well, if you are adding in the exponent, we can take the base and we can do 1/2 to the x times 1/2 to the first. Well, 1/2 to the first is 1/2. 1/2 times 8 is 4. So now we have 4 times 1/2 to the x power, which is the same thing we have right here. So this one is the same equation, just written in a different way. It's an equivalent form. So option 4 works. Option 5, using the same exponent rule, we can rewrite this as 1/2 to the x times 1/2 to the second. 1/2 to the second, so 1/2 times 1/2 is 1/4. So we have the 1/2 to the x power, but we have a 1/4 instead of a 4. So option 5 is wrong. Option 6, let's do a similar deal. 1/2 to the x times 1/2 to the negative second. 1/2 to the negative second is equal to 4. You can use your calculator to see that, or you could do, for this 1/2 to the negative second, you could do something like this. So this would be 1/2 to the negative first squared. And 1/2 to the negative first, that'd be 1 over 1/2, which is 2. And 2 squared is 4. So 1/2 to the negative second is going to equal 4. So that means we have 4 times 1/2 to the x, and that's going to match 3 and 4. All right. Option 7 here. So 4 over 2 to the x power is the same as 4 times 1 over 2 to the x power. 1 over 2 to the x is the same as 1/2 to the x, because if you apply the power of x to 1, 1 to the x power is just 1, okay? And now we've shown that it's the same thing, so that's correct as well. And then this very last one, option 8, I'm going to rewrite this as -4 times 2, and this negative x power I'm going to write as -1 times x. And I can rewrite this as 2 to the negative first to the x power. 2 to the negative first is 1/2, so we get the 1/2 to the x power, but we still have this -4 here, which is not correct. So it can be a little bit tricky. You got to know your exponent rules decently well, but if you have access to a graphing calculator, then you would graph them and see which ones overlap with the correct graph. All right, part F. The minimum wage in the state of New York has increased exponentially. In 1981, the minimum wage was $3.35 an hour, and in 2016, the minimum wage was $9 an hour. Part A, calculate the annual rate of growth in the minimum wage. So how much was the minimum wage increasing each year? That's what we mean by annual rate of growth. Annual meaning each year. Round to the nearest thousandth of a percent. So here's how I approached it. In 1981, minimum wage was $3.35. The difference in time from 1981 to 2016 is a 35-year difference. So if we're talking about a common ratio every single year, we have $3.35 minimum wage in 1981 times 35 common ratios. Imagine R times R times R 35 times. That's R to the 35th power. And that would eventually, if you do 1981's minimum wage times 35 common ratios, that would get you to 2016's minimum wage of $9. Divide the 335 on both sides. Now we have R to the 35th power equals this, and you take a 35th root to find out R for just a single year, okay? So you can either do a 35th root, or you can recognize that 35th root is the same thing as the 1 over 35th power. So 9 over 3.35 to the 1/35th power, that gives you 1.0286. So what this is telling us, this is what we multiply by every year. Okay, they're telling us this thing is exponential. So every year, it's multiplying by 1 point. The previous minimum wage is multiplying by 1.0286. Now, what this means, if the growth rate is 1.0286, we have the 1 here. That means 0.0286. That's 2.86%. You're moving the decimal twice to the right to turn it into a percentage. So it's growing the minimum wage by 2.86% each year. All right. So that leads us to part B. Write an equation for M of T, the minimum wage in the state of New York, T years after 1980. Common thing that you don't want to accidentally make a mistake with. In 1981, it was $3.35. This is T years after 1980. So we can't put the 335 as the initial value because this was already 1 year after 1980. So you can just take your 3.35 and divide it by 1.0286. That gives you this 3.257. So you just basically went backwards 1 year. And then we already know your base is 1.0286. That's what we calculated in part A to the T power. All right. Use your equation from part B to predict the minimum wage in New York in 2022. All right, well, 2022 is 42 years after 1980. So we're just taking our equation from part B and we're plugging in a 42 for T. Just put that in the calculator. You should get $10.65. And then part D, the actual minimum wage in 2022 was $13.20. How does this compare with your prediction? Well, it's Just like residuals, residuals are the actual value minus the predicted value. So the actual value in 2022 was $13.20 minus the predicted value, which we got from the model in part C, 1065. That gives us a difference of $2.55. So our predicted value underestimated the true value by $2.55. All right, part G. Aphids are very small, soft-bodied insects found on most plants in yards or gardens and that have an astounding reproductive capacity. A population of aphids gains 7/8 of its size every 2.5 days. Mara counts 53 aphids on a vegetable plant in her yard. Write an equation for a function a that gives the aphid population in Mara's yard, a of t, after t days. Okay, so initial population of 53, and this population is gaining 7/8 of its size. So 1 plus 7/8. Now, you could turn it into a decimal if you want to, but I went ahead and kept it as fractions. So to add 1 plus 7/8 together, notice that 1 is 8 over 8. 8 over 8 plus 7 over 8 is 15 over 8. And notice in the equation, we have t divided by 2.5, okay? Again, it's gaining 7/8 of its size, but it's every 2.5 days, not every day. So we're dividing by 2.5 to take that into account. All right, part H. Katerina works at an ice cream shop. She notices that on days when the temperature is higher, the store sells more ice cream. She tracks this data over the summer and notices a linear pattern that can be modeled by the least squares regression line right here. So this is the daily predicted sales in dollars when the temperature is X degrees Celsius. On a certain day when the temperature is 27 degrees Celsius, the total ice cream sales are $720. Calculate and interpret the residual. So again, residual is the actual value from your data minus the predicted value from your regression model. The actual value was $720. They gave that to us. The predicted value we have to calculate by just plugging in 27 degrees in for X. So the model will predict on a day where the temperature is 27 degrees Celsius that the shop will make $675.17. Go ahead and subtract those two, actual minus predicted. This gives you $44.83. So what this means is that the actual sales on this day where the temperature was 27 degrees Celsius, the actual sales were $44.83 higher than the predicted sales from the model. All right, part I, half-life of RF-265, an isotope of the element rutherfordium, is 13 hours. Write an equation for R of H, the amount of RF-265 remaining from a 500-gram sample after H hours. All right, half-life, this means our base is 1/2. Initial amount, 500 grams. It takes 13 hours for 1 half-life, so H over 13. Part B, write an equation for R of D, the amount of RF-265 remaining from a 500-gram sample after D days. So what I did, I took my function from part A, which is for every half-life, every 13 hours, and I went ahead and used exponent rules. So I did, instead of H over 13, I did 1/2 to the 1/13th power raised to the H power, and I got my function for every 1 hour instead. Now part B is asking after D days. So I rose this power, 0.948, to the 24th power, because there's 24 hours in a day, to get my new function that's going to represent for each day instead of each hour. All right, part J, kind of similar to one of the ones we did previously, towards the beginning of the quiz review. I noticed, I have this point 1, -9. I have this point -1, -81. If I just simply shifted my graph to the left by 1, then I would have a y-intercept at 0, -9, and I'd have this point over here shift to -2, -81. And I like to do this because it allows me to write an exponential function and then just take my exponential function and shift it how much I need to get the original graph. So to go from a y value of -81 times 2 common ratios, then I would get to a -9, okay? Because these two are two x values away from each other. So divide the negative 81, we get r squared equals 1/9. Take the square root of both sides, we get r equals 1/3. So before shifting it to the right one, so for this blue function here, the function would be y-intercept -9, common ratio of 1/3 to the x power. But that would give me the equation in blue. Now I just shift the equation in blue to the right one, and I can get this right here. -9 times 1/3 to the x minus 1 power. And this is just one correct version. There's multiple correct versions of this equation. In fact, the key from Mathematic has a different answer, but that different answer is equivalent to this one. All right, part K. Group of high school students started studying the number of Twitter followers of their favorite pop star. Linear regression was used to develop a model for the number of Twitter followers of the pop star in the years since 2010. The figure shows a graph of the residuals of the linear regression. Is a linear model appropriate for the data? Explain why or why not. No, a linear regression is not appropriate because when you look at your residual plot, you don't want your residual plot to have a clear pattern. We can see that the residual plot definitely has a clear pattern. It looks like the residuals have a quadratic pattern. So if your residual plot has a pattern, then the model used to make that residual plot was a bad model. So we used a linear regression for this. The residuals have a pattern, so a linear model is not appropriate. And then finally, I think this is the last one on the review. Oh, I forgot two problems. Uh-oh. Not the last one on the review. If S dollars are placed in the account earning 1.85% interest, compounding continuously, write an expression that can be used to determine the amount of money in the account after 15 years. All right, so compounded continuously, we use this function right here. S is the initial amount. This should not say E, this should say R. This is a typo on my part. T equals 15, so we just plug the points into the formula. Remember, E is about 2.178. So because we don't know the actual initial amount, we just told S dollars are placed. We can't actually calculate it. So it's S times E to the point 0.0185 times 15. Alrighty, let's try these out real quick. Forgot these two. All right, an exponential function of the form y equals a times b to the x power passes through the points 2, -3, and 5, -24. Find the values of a and b. Notice there is no horizontal shift. Okay, so immediately what I'm thinking, -3, notice that, so this is the y value here. 2 and 5 are 3 common ratios apart. So times r times r times r would get us to -24. Divide both sides by -3. -24 divided by -3 is 8. Take the cubed root. Cubed root of 8 is 2. Okay? Cubed root of 8 is 2. So if I'm thinking about like a table here, this is x, this is y. So we already know that 0, 1, 2, 2 was at -3, 3, 4, 5, 5 was at -24. And we know every single time from what we just found, we're multiplying times 2. So -3 times 2, that's -6. -6 times 2, that's -12. -12 times 2, that's -24. So we can just divide by 2 to go backwards. So -3 divided by 2 is -3 halves. -3 halves divided by 2 is -3 fourths. And I want to stop here because that's my y-intercept. So my equation can be y equals -3 fourths 2 to the x power. There's A, and there's B. All right. Okay, lastly, a patient receives a medication through an IV when arriving at the hospital. The amount of medication in the patient in milligrams after t hours can be modeled by the function A of t equals 12 minus 12 e to the -t thirds power. How many milligrams of the medication are in the patient after 2 hours? Round to the nearest thousandth. All right, well, let's just go ahead and we're just going to plug in 2. So 12 minus 12e to the negative 2/3 power. I'm getting 5.839. So a of 2, plugging 2 into the function, I got 5.839 milligrams. All right, part B, use the graph of A to describe how the amount of medication the patient is changing. So let's graph it. And you can graph in Desmos. I'm going to graph off the screen. All right, so it's looking like the graph of this exponential is increasing rapidly, and then it's going to start to decrease, or it's going to start to increase more slowly, specifically towards that horizontal asymptote of 12. So increases rapidly, but starts to increase slower. As we approach, and it'll continue to increase towards a value of 12. So it increases rapidly, but starts to increase more slowly, never exceeding 12 milligrams. What is the maximum dosage of this medication that the patient can receive? Well, the answer is right in front of us. Again, it can't exceed 12 milligrams. All right, y'all. I hope this was helpful. I'm ending the video here.